I'm not Chen, as Tom pointed out. He's eating croissants in Paris right now. So the title, as on the slide, is slightly a joke. It's because we're going to be dealing with ROIs, so there are no the clusters are pre-chosen, as you say, but it's related to the other poster that we have here, which is on clustering. So it's a, sort of an in joke. Let's see. This thing is too mysterious. So multiplicity is one issue that bedevils many different kinds of things. Multiplicity is not just multiple comparisons or multiple testing, because it has to do with the fact that we're doing a lot of stuff, whether you're talking about genes, but in this particular case, talking about the brain. And so it's not just saying multiple correction for multiple comparisons, which is the usual thing, but it's also has to do with just multiple reporting. I mean, you have to report a lot of stuff. And so, again, the particular example I'm going to give when I get to the data will be seed-based resting state correlation among from ROIs to a particular voxel. But the point is the multiplicity, and we're going to deal with that through a Bayesian multi-level model where we're dealing with ROIs, so that we have, and then we're going to end up reporting everything. We're not going to do any thresholding and report everything. And this is a kind of thing we're beginning to advocate, is that it's because something that is marginally, quote, statistically significant may be of interest to somebody, maybe not even you, but to somebody else interested in that area. If you thresholded it out, then they'll never know. So let's see, it's the correct button, right? So cluster failure. Someone here wrote a paper called, with that title, I can't remember who now, but basically, voxel-wise stuff is good. Voxel-wise stuff is good when you have less idea of what you're looking for, and you want to see what's going on in the brain. And the penalty for that is you have to do, because fMRI data is full of crap, that you can't do a voxel-wise thresholding and have very much survive. And so you have to do cluster-wise thresholding using contiguity, and then you have the problem there that, as somebody in the, sitting up here pointed out, that's difficult to do and control statistics adequately. And there are ways to fix that now, but there's a price for everything, and that is more stringency. If your false positive rate was 20%, to get it down to 5%, you've got to get rid of 15%. And so there are, so that's one way. The other way is to go to ROIs. But then we also still have the issue of the null hypothesis significance testing, NUST. So where the whole point of everything on this slide, everyone should know, at least if they're sitting in the audience, but the important thing here is the very last bullet point, which is the magic number 0.05, which was chosen, in the 1920s or something, right? And it says, 0.049, great, 0.051, ignore. And which is, of course, even the person who did this knew that this was absurd, but it was like you have to make decisions at some point. But it's not a good way to make decisions, really, after a century's experience, basically. And the world isn't dichotomous. I mean, guilt versus innocence is maybe dichotomous, although even that's kind of murky. But many things are not really dichotomous. The null hypothesis in the whole brain is kind of, a straw man, or as a certain current president of the United States would say, a witch hunt. And that is, it's something's, the brain's doing something. And false positive isn't really a good name for what's going on. Another problem with null hypothesis significance testing is that if you get a small p-value, you think this is more significant. And in fact, the word significant is wrong. I mean, it was a mistake on the part of Neyman and Pearson, I think back in the good old days, to say statistically significant. We should always say statistically significant, but it's such a long set of syllables, we would drop the statistically and say significant, but significant means important. But if I give you a drink to drink and say, we did a null hypothesis test on this and it was 0.06 that it's a neurotoxin, so it's okay, drink it. Would you drink it? You'd be nuts, you know? You'd probably sidle out of the room and never talk to that guy again, right? You know, so it depends on the goal, right? If it was but the probability that the small p-value or large p-value not necessarily mean significant. It may mean statistically significant, but it should have been a different word, though. I don't know what it should be. The phatic utterance. So, and again, 0.05, 0.051, so that was 54, 53. So cluster size 54, yes. 53, sorry, gone. You know, just, you know, it's this dichotomy. The old scientific literature approach doesn't make a lot of sense for neuroimaging or for genetics, for that matter. It's the same kind of thing, lots of stuff. And it's hard to do power analysis in fMRI because, I mean, pulse sequences are different, echo times are different, and so on, so that percent signal changes and all that will be different from scanner to scanner. Just how well the physicists take care of your scanner is different from site to site. So in the following, we have a bunch of equations which some people love and other people loathe and run screaming away or turn their minds off. Good Lord, it's presenting my slides incorrectly. So there are 124 subjects, resting state. There's a seed and the correlation to every place in the brain. And there's a behavioral measure, which in this case is a theory of mind index, which goes by the clever name here of X for each subject I. And then, so the measurement at each voxel, oops, I was trying to use that as a pointer and that didn't work. This is univariate GLM, and then clusterized every voxel. So we just fit this linear model of intercept and slope with respect to the behavioral parameter, and we're interested in, you know, where is the behavioral parameter important. And if you do this, it depends. Of course, this is the fun part of clustering. It depends on your per voxel threshold, for which there's no obvious good reason to choose a particular value. And you get anywhere from 2 to 4 surviving clusters. So, and then, which is, of course, an invitation to get the results you want, within reason anyway. So an ROI approach is the same thing, exactly the same equation. It's just on a fewer set of numbers, averaged over ROI, so hopefully they don't have so much noise in them. And then, of course, we have to still use our old friend Bonferroni to now, instead of clustering, you know, spatial contiguity, we have to use Bonferroni to correct for this. So we divide by, well, in this case, 21, because there's 21 locations. So the approach that Gong Chen developed, and so I'll take credit for everything and blame him for any problems. That is to use a very similar model. The first equation up here is the same model. That's just repetition, and so to make it easy to see the contrast, the Bayesian multi-level model has the following: the data for each subject I across each ROI J is again a slope-intercept model with respect to the subject level parameter, plus a random variable for each subject. In this case, that's put in. That you can think of that as allowing for global correlation in the gray matter that varies between subjects. But we see that this is something you see. You know, so all gray matter is correlated with all gray matter, but how much depends on which person, and maybe on how much caffeine they had even. And then of course epsilon ij, which is we'll pretend is a random variable. We're pretending everything's a random variable here. And that is, and then it's Bayesian. So we put priors on those, and then we put hyperpriors on those parameters, weakly informative hyperpriors. And this is Gong's wording. We don't fully trust the data. That is, the combination of pooling the variance estimates across the ROIs and putting in the Bayesian regularization of the problem. In this context, Bayesianism is using, not that we believe the priors as prior probabilities, but it's a method of turning a problem from not very well posed to a more well posed estimation problem. The penalty for that is, as is well known, is that the estimates for the thing we care about, B, shrinks towards the origin. It gets smaller. So the results, one of the results of the program is this, and which I would suspect that you find that difficult to read because I've been seeing a lot of people's slides with tiny little graphs and it really annoys me. So the next slide will fix that. But so we get this full report for the 21 RIs, which happens to be 7 by 3, which at least is not a prime number, so can fit in a grid, is that we have, let's see what one of those looks like, or 3 of those, the top 3 rows. For each region, like, so the top row, the right PCC, the right temporal parietal junction, and the right insula, we have the posterior distribution of the B for that particular region, and then is marked the tails of that at the 5 and 10% levels. And that you can see that for the right insula, 0 is nicely in the middle of the big white region, which means that most people wouldn't consider that statistically significant. And then you get all those plots, and then you also can get these plots, which are on the left, on the bottom are the 21 ROIs. So and then there's two bars for each one. One is the GLM, which is Bonferroni uncorrected, plus the 95% confidence interval, and the other one is the inner 95% region for the Bayesian posterior. And most of these, well, this isn't really a pointer, but you can see that the one on the left, remember, is the GLM for each pair, and the one on the right is the Bayesian, and that they shrunk. That is, you can see that on most of them, not all of them, the black line, the middle, is closer to the origin. On the other hand, the variance estimate shrunk more, if you want to put it in terms of variance, so that the width of the bars shrunk more, so that we see more things above that would be, quote, statistically significant. But another thing is that this is a full report on the whole result. That is, you can see, if you're interested in, that's the region, the LSFG, superior frontal gyrus, left. So that's the, 1, 2, 3, 4, fifth one in. You can see it would not be, quote, statistically significant, but it's up there. It's a hint, perhaps, that this is interesting in this problem. If this was reported, it could be carried through into a meta-analysis, someone else's paper, or someone else could just use this as saying, I really like that area, let me do another study, or something. But if it's just thresholded out, then they'll never know. And then, of course, the real report is all that's generated from tables. It gives you these tables, too, which I expect you to have memorized because there will be a test. All right, my time is up. So you also get, that's too bad. You also get the simulations of the data, random realizations of the data that come from the model. And the point of that is that from the GLM on the left versus the BML, which is hard to pronounce LM and ML in the same sentence. But you do that, and you see that the simulations realizations fit the data somewhat better, which is an indication that the model isn't at least insane. Well, you never know with Gong. So move. So advantages. Full reporting. That's to my mind. Now, I am not giving the talk that Gong will give. I'm giving the talk that I like. Okay, the full reporting is, I think, really a valuable thing here because it's not dichotomization. A person reading it, you can color them in to say there's the thresholded ones, but the uncolored ones may, for some people, be as interesting. and especially the fact that in some cases there really is no evidence of anything. It's pretty well centered around 0. In other cases, it's lopsided. Maybe it's just noise, maybe not. There are obviously concerns. This particular example only takes 5 minutes to run on a node at the NIH cluster, but if you throw in more data, more complicated models, and so on, then things get more complicated. Because it's using STAN, so it's doing a lot of stimulations, and the longer it takes, the longer it will. There's assumptions of exchangeability. It's impossible to do this in a voxel-wise level now, because it would be, there's a whole bunch of problems with that, actually. So that's it. That's poster number 2248, which if anyone really wants to talk to me, they can try and find me about this tomorrow. And or after this. This is in AFNI now, which this kind of gotten mangled up on the projection, but it's Bayesian group ana.py. And if you have any questions about actually using it, the message board or email. Email the Gong or the AFNI message board, because Gong is really, I like to make fun of him, but he's actually one of the most helpful people in my group. And that's saying a lot, because everyone in my group is pretty helpful. So thank you.